Hello class, in this lecture we will be beginning Unit 2. So this unit will cover chapters 5 through 8 and we'll be talking about compounds, chemical reactions, and how we work with those chemical reactions and various topics centered around those ideas. So our first chapter is going to be chapter 5, where we're going to be looking at compounds and the molecules that make up those compounds and various aspects of how we work with compounds. So one of the first things that we have to understand with compounds is this idea of constant composition. So what this essentially means, right, is that when we write out the formula for a compound, it is always going to be the same for that given compound. So, for example, a lot of us already know that water has a formula H2O, and it will always be H2O. It'll never be O2 or H4O or H2O2, right? Any of those formulas may represent some different compound, but that would be a different compound, right? So that's essentially what the law of constant composition implies. But if we want to write it out a definition, essentially what we would say is that all samples of a compound contain the same proportions of their constituent elements, which is sort of a formal way to say the formula for a given compound is always the same, right? So again, water is always H2O, carbon dioxide always CO2, right? So any sample of any given compound is going to have the same formula. Now, one of the things that, as we're learning about these various ideas, is we want to make sure that we understand the difference between a mixture and a compound, right? While we might have a mixture of elements, such as hydrogen and oxygen, notice those are not chemically bound together, right? It is simply a mixture, right? We have two different kinds of matter. We have hydrogens, we have oxygen, and they're mixed together. A compound, like water, which contains hydrogen and oxygen, if we remember back our definition of a compound, right, is that it's one or more different elements chemically bound together in a specific geometric arrangement, right? So we can see how the water molecules have the two hydrogen atoms bound to the oxygen atom in a specific way, and notice they're all the same. So we want to make sure and keep that distinction separate. So constant composition. Now, one of the ways that we can mathematically show this constant composition is to look at the mass ratio. So what implies if we have constant composition is that any sample of that given compound will have the same mass ratio between the elements in that compound, right? So if we always have the same number of hydrogen and oxygens, or carbons and oxygens, right? So if we're looking, then the masses should always be, the ratio of the masses should always be the same. So, for example, if we take one sample, and that sample is 6.6 grams, and we break it down, and we get 4.8 grams of oxygen, and we get 1.8 grams of carbon. Notice conservation of mass, right? 6.6 grams to start with, 6.6 grams to end with. But the ratio of oxygen to carbon is 2.7. If we take another sample of presumably that same compound, right, it should have the same mass ratio no matter how much of that compound we start with. So let's say we start with 23.5 grams. And we break it down, right? It ends up with 17.1 grams of oxygen, 6.4 grams of carbon, and notice that ratio is the same. And this becomes a way that we can show or prove that a compound is what it is, right? Later on, this will be more formalized in something called mass percent composition, and we'll work with that a little bit later. And so, by knowing that we have the same mass ratios, we can show that it is the same compound, right? This idea of constant composition. Now, when we express compounds, right, we have to write them out. We write them out as what we call a chemical formula, right? Now, there are different versions of chemical formulas that come up in different aspects. Now, the most familiar to most of us is what's called the molecular formula, right? This describes what's actually there. So when we saw previously, when we wrote H2O, that is the molecular formula, right? It tells me that every molecule of that water molecule, of that compound water, has the formula H2O, 2 hydrogens, 1 oxygen, right? That is a molecular compound. It gives the actual number of atoms of each element in the molecule of a compound. Now, another type of formula is called an empirical formula, right? This gives the relative number of atoms of each element in a compound. So it's sort of the simplified version, if you will. So, for example, if we have the compound hydrogen peroxide, which has a molecular formula of H2O2, it would have an empirical formula of HO, right? So we're reducing it down to sort of the lowest common factors, right? So it's the simplest ratio of the elements in the compound represents what we call the empirical formula. Now, in a lot of compounds, the empirical formula and molecular formula are the same. So water, right? This is the molecular formula. It's also the empirical formula because you can no longer reduce it down to a smaller whole number ratio. So in some compounds, they're going to be the same. Now, for what we will call molecular formulas, right, or molecular compounds, right, these are going to be the molecular formulas that we're going to be dealing with most often. Now, one place where empirical formulas become important is when we deal with what we call ionic compounds, which we'll talk about here in a second. And it is the empirical formula of these ionic compounds that we use to represent them. Now, a last sort of type of formula that we'll see is called a structural formula. And this comes in different sort of versions. The simplest version is this sort of line and stick model. And the basic difference is the structural formula gives bonding information. So it tells you how the molecules are bound to one another. Right? Now, most times when we deal with formulas, we'll be dealing with molecular or with empirical if we're dealing with ionic compounds. But oftentimes, especially a little bit later on, we'll write out structural formulas because it'll help us understand the connectivity, how they're bonded. And there's various versions of these. You can go up to things like what we call ball and stick or space filling model. They give you more three-dimensional information, right? They give you more information on shape. So structural formulas tend to be flat, right? We draw them out in 2 dimensions. A ball and stick or space filling or 3-dimensional structures. And so they give us 3-dimensional shapes. They give us a little bit more information. Now, we won't typically ever draw these. We'll see them in books, and they'll help us understand something about the molecules when we work with them. So at this point, we're going to take a couple minutes to revisit our flowchart for when we separated material or matter by composition. And so we're going to look at the pure substance side of that flowchart for a couple minutes to sort of review a few things. So remember that those pure substances were divided into elements and compounds. Now, in the last chapter, we focused on atoms and elements. And one thing we'll sort of add to that is the idea that elements sort of come in two big types, right? There are elements that exist as what we call atomic elements. So the simplest or the stable form of those elements is individual atoms. Now, this is most elements exist this way. So we have things like mercury or neon, right? These exist as individual atoms. That is the simplest unit. Now, there are a few elements that exist as what we call molecular elements, meaning their stable, normal form is more than one atom bound to each other. So you're familiar with this, you may not realize it, but when we talk about, say, oxygen, right, we always talk about O2. Right? That is the stable form, two oxygen atoms bound together. Now, there are a few important elements that exist this way that we need to understand and we need to really memorize so that when we work with them in reactions, we understand that they're always going to be written out in what we call that diatomic form. So those 7 elements are known to a lot of us already, but they are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodide, right? The halogens here. These all exist as diatomic molecules. So while they're elements, when we write them out in chemical reactions and so forth, we're going to write them out in their stable diatomic form. Now, there are also a few elements like sulfur and phosphorus that actually have stable forms that are bigger than this, but we don't need to really worry about that for this class. So let's look at the other side of that flowchart, the compound side. So now compounds exist in 2 different types, right? Or we're going to learn about 2 different types of compounds, right? We have molecular compounds and we have ionic compounds. So big difference is, again, what their stable form is, how they exist. So in a molecular compound, they exist in individual molecules. So this is the type that we're often familiar with, like water and carbon dioxide, right? They exist as a whole bunch of individual molecules of that formula, right? So when I write out H2O, I know that that contains a bunch of molecules that have the structure H2O. So this is called a molecular compound, and this represents the molecular formula of that compound. Now, ionic compounds, these are compounds, as we'll learn, that are made up of ions, right? Typically, a metal positive ion. Remember, metals like to form these positive ions. They like to lose electrons. And a negative non-metal ion. Remember, those non-metals like to gain electrons and form negative ions. So ionic compounds are made up of positive and negative ions come together to form a compound. Now, as we can see from the picture here, ionic compounds don't exist as individual molecules. There are no individual molecules. So, for example, probably the most well-known ionic compound, right, sodium chloride. Right, we write it out as NaCl, but there is no NaCl molecule, right? It doesn't exist, right? Sodium chloride exists as what we call a 3-dimensional lattice, right? Where we have this big structure of sodium ions and chloride ions. The way that we write it out, the formula that we write, is called the formula unit, right? And it is the simplest neutral formula for those compounds. So because sodium has a positive 1 charge and chlorine has a negative 1 charge, the simplest way that we can write out that in a neutral, charge neutral way is sodium chloride. 1 sodium ion, 1 chloride ion. And that's how we write out ionic compounds, right? When we write them out, we represent them as their what we call formula unit, right? That simplest neutral formula. Now, as I mentioned on a couple slides ago, this is also what you might refer to as an empirical formula, right? It is not representing what we actually have. It's representing the simplest whole number ratio of the elements involved. We're going to start our looking at how to write out formulas and eventually name formulas by looking at how we can write out ionic formulas. Now, ionic formulas we have a little advantage of because of the ions that are present, right? By understanding what ions are present, we can then put them together in a neutral way to give us the formula. So knowing the charge on those ions really lets us to simply write out ionic formulas. So we're going to do that a little bit. So a couple things to remember. It first thing goes back to, this is one of the reasons why you should be working on memorizing those common charges that we talked about last chapter, right? Where we need to know what charges certain groups on the periodic table form, and understanding that when we write out the formula, it must be charge neutral. All right, we must have the same amount of positive and negative charge. So let's try a simple example with combining magnesium and oxygen, right? And the idea is, what formula would the ionic compound between magnesium and oxygen take on? Well, the first thing that we need to understand is by knowing our common charges, right? We're going to know that magnesium, being in group 2, is going to form a 2+ charge. And oxygen, being in group 6, right? That group always forms a 2- charge. So when we put these together, right, the simplest way to make the charge balance out is, because they're the same charge, right, is a 1-to-1 ratio. So the formula for magnesium oxide is simply going to be MgO, right? That is the formula unit of the ionic compound between magnesium and oxygen. So pretty straightforward. Now, one complication that does come in when we write these ionic compounds is that not all ionic compounds are simply between elemental ions, right? Not simply between the ions formed by elements on the periodic table. Some ionic compounds contain what we know as polyatomic ions, right? These are ions that contain more than one atom. So these are, in other words, these are groups of atoms that take on a charge. Or an ion that contains more than one atom. Now, unfortunately, I wish I could tell you there was an easier way to do this, but we simply have to memorize these. And when I say memorize, I mean the name, formula, and that formula, of course, includes what the charge is, right? So we have to know that carbonate, right, is CO3 2-, or we have to know that nitrate is NO3 -1. I would, advise you to start working on this as soon as possible, right? Yeah, you'll need to know these by the exam, right, on this unit. And so flashcards, Quizlet work really well to just memorize these formulas and charges, right? Now, one thing you'll notice when you look at this table more closely is that almost all of these ions are negative ions, right? So they are going to substitute what would be the non-metal in our ionic compound, right? The negative ion. Now, there is one exception to that, and that is the ammonium ion, right? It is a positive polyatomic ion, and it will take the place of the metal in our ionic compound. Right? Okay, so we want to work on memorizing these polyatomic ions. We're going to work with them as we go through these in different examples. So let's close out this section with a little bit of practice. So first one is write the formula for the compound that forms between strontium and chlorine. So in your process of learning these things, right, we need to become familiar with these elements. And so strontium, right, if we look on the periodic table, right, that's in group 2, right? So we know strontium being in group 2 is going to form a 2+ charge, right, the symbol Sr. And we know that chlorine, being a halogen, right, is going to form a -1 charge. So there's a couple ways to think about this. Now, for some of you, it'll be really straightforward to look at this and say, okay, I have a +2 here, so I need to have a -2 to balance that out. Well, each chlorine is -1, so if I have 2 of them, that'll allow me to have a total of a 2- charge to balance this out. So the formula is I need 1 strontium for every 2 chlorides, right? This will be my simplest neutral formula. So +2 from the strontium ion, -1 from each of the 2 chloride ions to balance it out. Now, a little shortcut or a little trick you can use is if you look at the charges, they become the subscript or the number of the opposite element. So we see that the 2 here becomes how many chlorines we're going to have. The 1 here becomes how many strontiums we're going to have. And we end up with, of course, the same formula, SrCl2. So either way, the key is that we get to the right neutral formula. Okay, let's try one more. We have aluminum, right? Aluminum is in group 3, so it's going to form a 3+ ion. Now phosphate, right? This is one of our polyatomic ions, so as we start to learn these, this is going to be PO4 3-. Now, if we're putting this together, now we might be able to easily see this is a 1-to-1, but I want to point something out here, and that if you do use this trick, right, where you pull these down, and you might initially write Al3 PO4 3. Now, we don't want to leave it this way, right? We want the simplest whole number ratio of the ions to give us a neutral compound, right? That's our empirical formula, our formula unit. So the simplest, right, is to reduce those down to 1 of each. So +3 here, -3 here. So the simplest way to write this out is AlPO4. Right? So while this is the right ratio, 1-to-1, right, it's not the simplest way. And so we want to make sure to write this as the simplest way. So again, with all of these things that we're going to be doing throughout this chapter, practice, right? So the more practice you can do in writing out these formulas, these ionic formulas, the easier it's going to become. So next time, we will keep on this and we'll learn how to name these, right? How do we name these formulas?